really, we dig into the details, and it is so important. And you know, it's at the end when you're looking at the data and you're like, oh, I am so glad that we made this choice. And so that's, you know, sort of one of her signature, you know, foci is, again, and it's a very difficult tension to navigate. She studied messy problems in messy contexts, determined to find some simple truths that could be applied. Simple truths that could be applied. She focused on the dual diagnosis of mental illness and substance use, medication polypharmacy and switching, how to use claims data to improve care. She was an incredible and is an incredible leader, a chair of too many committees to count, and a common theme in her research, again, has been creating scalable ways to implement new services, monitor implementation fidelity, and measure outcomes to assess the extent to which the intended services are indeed those being delivered. Dr. Essock thus endowed the Essock Lecture to be given to a mental health scholar whose work exemplifies one or more of these components. So I just want to acknowledge Susan, who's here. And obviously, Susan is the person who brought me here, and I am really forever grateful to you, not just for the mentorship, for the collaboration and the partnership, and for endowing this award. So, now to get to Dr. Wall. Dr. Wall is the first awardee. She is the director of the Division of Mental Health Data Science, which got its name starting in 2018, in the Department of Psychiatry here at Columbia and the New York State Psychiatric Institute. And I dare say that if there is anybody who is more deserving of credit for the success of many of us in this room here right now, I don't think there exists such a person. Dr. Wall has contributed to the success of so many of us. Dr. Wall received her BS in mathematics from Truman State University in Kirksville, Missouri, an MS in statistics from Iowa State, and her PhD at the same. She's definitely a Midwesterner. She went on to join the faculty at the University of Minnesota School of Public Health, where she became a tenured professor in 2010. At that time, she was recruited to be a full professor with tenure at the Mailman School of Public Health in the Department of Psychiatry and the Vagelos College of Physicians and Services here, and she took over as division director in 2012. Now, this is where it gets challenging to communicate all of what Melanie has accomplished. She is currently listed as a co-investigator or PI of 18 NIH grants and dozens before that. She has published more than 330 articles in peer-reviewed, high-impact journals and counting. As a teacher, she has won numerous awards. She lists 7 semester offerings of latent variable and structural equation modeling for health sciences. And she's actually playing hooky from teaching right now, from teaching over at Mailman. I wanted to just read you some of her invited talks to give you a sense of the breadth of her expertise. Shared versus specific effects of psychiatric treatment on multiple outcomes in clinical trials using latent variable modeling. And these are invited talks. Empirical methods for identifying optimal diagnostic criteria for psychiatric disorders, correcting for time-dependent measurement error and differential selection bias when estimating trends in marijuana use and disorder, a data-driven method for deriving shorter DSM symptom criteria sets, the case for alcohol use disorder. I mean, it's just like, when you start to read it close together, it sort of begins to sound like a lot of compressed words, but what I want to talk about next, very briefly, is what our faculty have said about working with Melanie and why we are so pleased to give her this award. So I asked some of her collaborators to tell us, to share, you know, what is so notable about Melanie. I'm going to read you some quotes from some of the responders. It is exceedingly rare for a statistician to have a keen sense for how to ask important questions of research data. Melanie has this uncommon quality. Across a wide range of topics, she's able to look at data with a fresh sense of what they might reveal about meaningful questions. More important than helping me to better understand structural equation modeling, confirmatory factor analysis, and when to use additive or multiplicative interaction terms, and this is beautiful, she has the ability to frame analyses in a way that reveals the answers to questions that matter. And so, you know, that I think just is, that is the engine that is, you know, perpetuating all of our research forward that Melanie offers. Melanie has so many strengths, but I believe one of her greatest gifts is her ability to translate complex statistics for behavioral health clinicians and scientists who may not have strong statistical backgrounds, me, but also to translate findings in ways that have clinical and practical meaning, and thus the Essock Award, right? She also, unlike many in her field, understands so much about all aspects of study design so that her contributions go way beyond just the analytic plan, resulting in studies of the highest quality. And I think what you hear is she will participate from the beginning and turn a good study potentially into a great study, a marginal study into a fundable study. And this is very, very precious. I want to read everything that people wrote, but I'll do a couple of more. I think it would be easier to list aspects of my work Melanie has not been involved in. As a general point, I would say that no matter how insanely busy or overstretched she may be, Melanie is always the kindest, most patient, smartest, and all-around most helpful collaborator I have ever worked with. I am always amazed at her generosity and how willing she is to meet and discuss projects with me. For nearly every other subsequent grant I received, Melanie has discussed the scientific question and study design with me from day one, then worked with me to design an appropriate analytic plan for data ranging from clinical to neurocognitive to brain imaging and others. And then finally, she is so smart, gets the problem in a, I'm embarrassing you, I know. I love it. She is so smart, gets the problem in a nanosecond, and offers pragmatic and innovative solutions. She is always ready to engage in the question and thus uses stats in the service of public health impact. Again, why she's perfect for the Susan Essock Award. She can explain complex stat models in lay language. She is really fun to work with. She is real, direct, and honest, and no nonsense. And from my standpoint, she's brilliant, practical, clear, demanding, rolls up her sleeves, and one of the very first things I noticed about her is that she is utterly respectful to every single person in the room, everyone around the table, whether it's a student, a research assistant, a faculty, junior faculty member, or a senior faculty member. Melanie treats, and it is so notable and it is so wonderful to be in the presence of someone who treats people the way that you do, Melanie. So I'm really pleased to be able to give you this award, and I thank Susan for creating the award so that we can honor people like Melanie. And I'm going to give you a little plaque. And then you can give your talk. Right.
Could you guys just stand together since I'm doing this for... Thank you. Great.
Thank you. I did not expect that introduction, and I don't even know how to follow that introduction now that the expectation is way up here. My goodness. First of all, I want to say there's seats up front. If people who are standing in the back want to come up front, I always come to this late, and I'm one of the few people who's willing to come front, and I think, please come, there's plenty of seats up here. I just want to say how grateful I am to have received this award. I'm very grateful to have had the opportunity to work with Susan, as well as to work with Lisa and many of you in the room. And I think the best way for me to follow that is just to sort of get started. So I put together when I was asked to give this talk, Lisa said, you can talk about whatever you want. And I thought what would be really good is to have the opportunity to try to speak to the Institute today about this new area of machine learning that we hear about all the time in presence of big data and so forth, and how I believe that we can think about how it fits into the type of research we're doing, and to really start a conversation. I'm not standing before you here as the expert in machine learning. It's a tool that, as you'll see, I think we can use in different ways. But I don't have a stance, and I want to sort of have this to be the start of a conversation about how we can use it more in our research. This is a quote from a very recent piece in JAMA Psychiatry that I want to read to you. That is that our realistic hope is that big data and predictive analytics, which as you'll see I refer to as machine learning, might deliver useful help with challenging decisions. We can already point to some tools that should prove useful as long as the users of those tools start with reasonable expectations, ask the right questions, and keep both hands on the steering wheel. And I think that's sort of a nice general theme for what I'm hoping to present to you today. So before we get into machine learning, I actually want to talk a little bit about scientific research so that we can frame where machine learning sort of fits into that. And to do that, I want to first start with Susan Essock's first paper. I, too, asked to look at your CV, and I, too, was impressed. And I thought how nice it would be to start off this, where I talk about scientific research, with your first paper where you studied pigeons. So in 1974, Susan published her first paper that's on her CV anyway. You might have had a prior career to that, I don't know, but where you did an experiment on pigeons. And I'm not going to go through too much detail of it, other than to sort of lay out how we can think about this study in the broader realm of scientific research. So there was a general research question, which was, does changing the schedule of how food is presented to the pigeon from fixed to variable cause the pigeon to sort of work harder to get that food? And the study design was a controlled experiment. There were 4 subjects, and I read the paper, and they keep referring to the pigeons as subjects throughout the paper. This is the data for subject 2, subject 4, subject 5, and subject 3. So there were 4 pigeons in this study. And the measures were pecking rates, and then there was a few experimental conditions, the variable feeding and the fixed feeding, and then there was time, and I'm not going to go into the details of the time component in the learning phase. But what I want to point out is this was a small data set with a well-controlled experiment, and the stats that are in this paper are really these graphs, which are really well-organized graphs of individual level data that pretty much answer the question directly. That is, indeed, the variable feeding rate in nearly every of the 4 birds at any of the time points had faster pecking rate. That is, they did indeed work harder to get the food when it was coming on a variable schedule. So the result was evidence to support this causal hypothesis that changing the way the food is presented would change the behavior. Then we turn to a second study. This is, I think, 35 years later from the first one by Susan. And actually, many of you in the room will recognize this study because I think many of you in the room were participants either directly in the paper or on an expert panel that you had assembled of people to help contribute this. So we go from small data, and N of 4, to a really big data problem here. And I'm going to define big data as we move on. But a big data where we're using electronic health records. But let's see what sort of the key features of this particular problem are. Here, rather than answering a causal question, the research objective was really to provide a description of prescribing practices. The study design was a very large cohort, very well-articulated cohort of people with 1 or more continuing prescriptions of a psychotropic drug for more than 90 days, and then very carefully described measures. And so that's where the expert panel came in. Susan assembled an expert panel to adjudicate what would be considered a sort of problematic prescribing practice. And this big table over here is just some of the 50 different criteria they came up with what would can be considered a problematic practice. And the thing I want to point out there is that was investigator-initiated description of variables from what could be over millions of possible ways to combine information from the codes that are in the Medicaid administrative database. At the end, the statistical summary is proportions, simple proportions, but proportions of very well-constructed variables. Snippet of the results here, so sort of the headline things was that 14% of people who were receiving a second-generation antipsychotic were actually receiving more than two or more, and that over half of those had not received a metabolic screening in the past year, those who were at high risk for metabolic. So this is a paper or a research project that represents an effective description of data that was able to provide a context for potential future policy decisions. And I want to say that in scientific research, we can think of there being sort of three general buckets of things we want to do. That is, we want to do explanatory modeling, that is trying to find out the causal effects that are underlying the things we can see in the world. Why does something happen? What are its causal effects? We can do description, what is happening or what is there. And we can think about doing prediction, asking questions like, what is the likelihood of something happening or something being true, given that a set of other known things are true? So how does big data and machine learning come into this? Well, into these three main objectives of scientific research, what I'm going to present to you today is I really think that big data and machine learning have a lot of potential to help us with description and prediction. That is, it's really entered as a tool that could be useful in that realm. And hopefully, eventually, will help us lead into explanation and causal understanding. So let me just go through what I mean by those three buckets and to make more crystal clear how machine learning is going to come into them. So first of all, in explanation and causal understanding questions, so I gave Susan's example of the pigeons. There we're interested in understanding a causal question. So in this case, does a feeding schedule, but in general, does a policy, therapy, exposure, drug cause a change in a behavior, a symptom, or some kind of biology? And then we know that now NIMH is actually particularly interested in getting us to think even more deeply about those kinds of causal questions and mechanisms, as if you know that it's causing it, tell us why. And so that R61, R33 mechanism is actually geared straight for doing that sort of thing. This type of question is really a traditional type of question we've been doing in scientific research for a long time. I would say it's the dominant objective of most scientific research in academia. The idea being that you might develop or motivate a theoretical causal model of how things work. It really represents a lot of what Lisa referred to as the projects that I have been participating in with many of you, and here I just give a list, and this is not even close to an exhaustive list. I just thought of the first 7 projects I could think of that I'm currently working on that really would fall under this bucket of studies with the objective of some kind of causal understanding. So, for example, a study looking at marijuana laws with Dr. Hassan, where we're wanting to see if those changes in the marijuana laws are causing increases in cannabis use disorder. With Mark, looking at the healthcare policy and how that is potentially causing changes in treatment for mental health and substance use disorder. With Milton, an implementation study where we're looking at mental health care implementation strategies in Mozambique and how different strategies for implementing it might lead to better mental health screening and access for treatment. With Tom, discharge planning, we're trying to look at whether if indeed when being discharged from an inpatient hospital, better planning practices are done, can that lead to reduced readmission? A POMA study, I think it was last week, Jeff was here and talked about all the work he's been doing with POMA, clinical trials there, looking at whether giving this drug reduces psychotic symptoms. Exercise study with Scott Stroop and David Kimmey, who's now left, looking at whether that could improve cognition. study with Sandy Comer looking at different types of naloxone education and whether that can decrease opioid overdose. So this is just a small snippet of the different types of causal questions that are being asked by a lot of the research we're doing. Okay. But description is also important. And I think it's becoming, with RDoC, it's becoming even much more important. So what do I mean by description projects? So what is there? So with a description project, like what Susan had done in the Medicaid claims data, we provide a summary of what's the current reality. So here we provide context and targets for further studies to eventually help with the explanation and causal understanding. So one area where a lot of people are doing work is trying to identify candidate biomarkers. So that is which characteristics are actually different between patients versus healthy controls. We're not particularly interested in the causal part of that when we're first asking the question just to find out what are the differences. So it's a descriptive problem to start. The causal thing will come afterwards. And then, psychopathology phenotyping. So we all know that the heterogeneity is basically a key feature of all the psychiatric disorders. And a motivation of RDoC was to try to sort of encourage the field to consider potentially new descriptions of those, new descriptions of the ways to phenotype psychopathology. And examples of projects that we're here at PI where we're working on that I would describe as, at their base, basically descriptive studies are a project working with Brett on cognitive and neural mechanisms related to PTSD, one with Blair where we're doing neurocognitive studies for OCD, and then with Raggy and Larry doing sort of similar deep phenotyping of early stage psychosis. I think we've all seen this figure for RDoC, the aim being to effectively improve a description of psychopathology. So by collecting data from all sorts of domains, rather than just symptom criteria in the DSM, we might be able to get a richer description of the psychopathology. So the idea here then motivates this sort of insertion of the term big data. So what do I mean by big data? When people talk about big data, they don't just mean a large sample size. It really has been described, and actually the evolution of the description is keeps adding on V's. So originally there was the three V's of big data, and the three V's of big data started off being volume, that is, it is about the sample size and in the size of the actual files that collect the digitized data. Velocity, that is how quickly you're able to get updated data. Variety, and that's really, I think, maps nicely onto the RDoC idea. That is, we want to consider all types of different domains that we want to measure. And then a fourth V was added, which was veracity. So once people started conceptualizing all of these together, we realized that the quality of the measures from the different sources might be very variable. So part of big data is dealing with very variable quality of the data itself. And some people have even added a fifth V, which is value. So how do all these things actually add value? I've listed here a host of things in psychiatry that we measure that would be part of big data. So, of course, clinical symptoms, but then all types of brain imaging, PET, fMRI, MRI, MRS, DTI, neurocognitive tasks that we can measure on people around sensory processing, cognition, wearable devices. So now, our smartphones can keep track of so much about us. How can we use information from that, which we could refer to as passive sensing, or other types of sensing devices we might an iWatch that might keep track of someone's heart rate, et cetera, as well as active devices that are prompting us to answer questions. Natural language processing of both speech and of text. Electronic health records, like the one that Susan had used with the Medicaid data. And then a whole host of things we can collect on life experience and social and cultural, environmental measures. And then, of course, under the skin, the biological data, like the genomic data and inflammatory markers. So the question is, how can we use all this big data to say something about psychiatric research problems? Well, I want to step back for a second and describe where machine learning sort of really started to come into the field. So this is a classic paper. It's only 18 years old, but it's really sort of was a classic paper where a statistician, Leo Bremen from Berkeley, sort of introduced the idea of how we want to start to think about how machine learning can be useful for us. So he said, okay, how do we describe the two goals of analyzing data? One is that we've got this sort of true thing out there, which is nature, and you've got inputs and outputs. And one of the goals, given some inputs and outputs, is to try to extract some information about nature, to try to learn something about how nature really works. But he said another goal is actually prediction. That is simply to be able to predict what the response Y is going to be to a future input X. And he organizes those two goals into sort of two different cultures of how to think about modeling data. The first being what he refers to, he actually calls it data modeling. I think explanatory modeling maps better onto the sort of goals of scientific research. So you have explanatory modeling, where we're in this framework over here, which some people have referred to as sort of traditional statistical modeling. I want to make the argument that all of this is statistical modeling. It's just different tools. So where here we might have some hypothesis that we're going to test, null hypothesis for beta being significant, we're going to test it different from zero. We're doing that because we want to somehow explain the nature. Another culture is, you've given some X, you've given some Y, just forget about the box. Just try to see if you can predict Y. So he refers to that as the algorithm modeling culture, which we can now refer to as the machine learning modeling. So there, we ignore nature and we focus on accurate prediction using all information available. Well, there's a lot of prediction questions in psychiatry. Prognostic questions. What's the likelihood that this patient is going to recover? What's the likelihood that someone's going to try to commit suicide? A lot of diagnostic questions. Can we classify a subject with a particular disorder based on objective measures like neuroimaging data? Precision medicine. Who are the patients for which a particular treatment is going to be best? What's the best treatment for a particular patient? These predictive questions, scientific research questions, really lend themselves to these machine learning methods. So how does machine learning fit into statistics? So I have, I think Lisa mentioned that recently we changed the name of our division from the Division of Biostatistics to Mental Health Data Science. And I think I did that mostly to reflect the fact that we embrace all kinds of methods for analyzing data, and machine learning is just another method for analyzing data. So we can think about data science and machine learning within this schema here, where we have this oval here being math and statistical knowledge. And what we've been doing in sort of traditional research is this intersection here between using statistics to answer questions about substantive or theoretical causal questions and trying to use data to do that. And that's where we've been for a long time. But then hacking skills here is meant to represent really all the different ways that we have digitized data and have to come up with hacking ways of sort of pre-process it, come up with some way of combining it, okay? So the red oval here can really be thought of as computer science and the digital revolution. And so as that intersects with math and statistical knowledge, there's a field called machine learning, which was really how to take statistics and use it in the presence of these really large data schemes. Sometimes this gets a laugh that if indeed you have just the knowledge about how to get the data and some substantive expertise, but you don't have the math and statistical knowledge for doing it, you're sort of in the danger zone. So this is the way I promote the need for statisticians. Okay. And just to clarify how I want to think about machine learning is it's really just another thing in the data science toolbox. So, the term statistic simply means a summary of data. So statistics, in general, encompasses machine learning because machine learning is a way to summarize data. So I don't like this false dichotomy, in my opinion, of like statistics versus traditional statistics versus machine learning as if they're somehow different things. It's just another tool in our toolbox. And so here I list all sorts of methods that you're familiar with that we would use in different types of studies, and another one is machine learning. So let's talk about machine learning. All right. So machine learning really did get developed in the 80s as a sort of collaboration, if you will, between computer science and statistics. If you go to the statistics journals, you'll see a lot of development in what are now called machine learning models, as well as in the computer science literature. They were a bit parallel, but also overlapping. And the idea is that it's concerned with the design of algorithms that allow the machine, the computers, to learn from data or learn from examples. The emphasis is on fully automatic methods. They're often algorithm-oriented. Focuses on computational tractability, like being able to do it fast. They're typically not concerned with things like statistical power because they're not interested in testing any particular hypothesis. We talk about statistical power when we're interested in testing a hypothesis. There's not a hypothesis per se being tested. Because the goal is not really interpretability, but on accurate prediction. And we all see the headlines. Machine learning has had some really impressive success in complex prediction problems in other fields. We all have iPhones. We know that Siri can hear what we're saying. That's a machine learning problem, speech recognition. Image classification, handwriting, recommender devices. You get ads all the time that seem like really good ideas because you've maybe been Googling something and they figured out what would be good to recommend to you by using machine learning algorithms to do that, predicting what you would buy next. All right, so we've also heard the term AI, and I think it's useful to understand how machine learning fits into this bigger picture of AI. So AI, as just a general term, is that trying to get machines to perform tasks that are characteristics of human intelligence. Okay. And machine learning is one tool for how to do that. It's one part of building something that will have AI, artificial intelligence, is being able to teach the machine to learn from data, which is basically what you're doing when you're doing predictions. So in an attempt to just give an example of something that's AI-ish, I found this, I'm not promoting this at all, but there's a new app you can get called TESS that's being promoted where it's basically a psychotherapist. So let me jump to the study about it. So it says TESS is a psychological AI chat box designed by this company to deliver brief conversations in the form of integrative mental health support, psychoeducation, and reminders. And then they go on to say, like, calm down. TESS serves as a therapeutic tool, but it's not intended to replace the role of a therapist, okay? But if you zoom in and see what this conversation is here, it is indeed the person saying, how are you feeling today? The person says, I'm feeling unhappy. And then an algorithm suggests what should be the response to the person. And so you're having a conversation essentially with a machine. So that would be an example of AI. And it's using natural language processing, which is a machine learning model, to suggest what the test should say back. All right, so in terms of machine learning, there's a whole host of different types of machine learning methods. They can be categorized in this way as supervised learning and unsupervised learning. I like to describe those generally as supervised learning being fancy prediction methods, so fancy regression, and unsupervised learning as fancy cluster analysis. Okay, so in terms of just thinking about it. But so supervised learning, you're given a bunch of predictor variables, the X's, the features as they call them in machine learning, and outcomes, the Y's, or in machine learning they're called labels, on a group of individuals, and you want to predict what the next individual's outcome is based on features. There's also an area referred to as reinforcement learning, and I think conceptually it's useful to think of that as like supervised learning over time with feedback and penalty. So you sort of put the supervised learner out into the field and let it learn on its own by creating some kind of penalty function for getting things wrong. And in unsupervised learning, the labels are unknown. So we want to learn the inherent structure of the data without explicitly provided labels. It's useful for description, feature construction, and pre-processing. And why? Because it can identify and collapse empirically similar structures in the data. Machine learning algorithms come in many flavors, and I'm not going to go into a ton of detail about these different ones because of that very nice long introduction. But we can think of penalized regression methods. So here, names such as lasso and elastic net you might have heard of are basically fancy regression methods. The other methods are a bit different, and I'm going to describe them in the next slide. But the other methods are taking different approaches than regression to try to do prediction. In tree-based ensemble methods, we're basically fitting many trees to a data set and then sort of aggregating across those. There's classifier methods like discriminant analysis, which is actually an old statistical technique, and an updated version with support vector machine. And then artificial neural networks and deep learning, which we hear a lot about in the popular press. So those different methods can really be seen as ways of addressing the limitations of just using regression for prediction. Everyone in this room has heard of regression before, and you know that you can get beta coefficients and test those, but you can also get a predicted value out of a regression. So why not just use regression for prediction? Well, what if there are hundreds or thousands of predictor variables? You run into trouble when the number of predictors you have is more than the number of samples you have. And what about if it's very nonlinear? Well, those penalized regression methods deal with that first problem, and they were very successful in the early genetic studies and GWAS in terms of identifying SNPs. So this method of machine learning was really advanced, motivated by the GWAS studies. But then what about if it's not linear? Well, the tree-based support vector machine and neural nets are very flexible functions that can do very well for prediction, but as I'm going to talk about, they need some very careful thinking in terms of tuning them to work in testing data, that is in externally validated data. And also, because they're black box predictors, there's no automatic variable selection. So they're going to be difficult to do explanation. I felt like it was important in front of a room full of psychiatrists, where we like to also study the brain, it would be important to show you why we call it neuronets. Okay? So it's motivated by the neuron. That is, so a neuronet, which is one of the type of flexible models, takes a bunch of data, actually just takes a linear combination of that, but then takes a nonlinear function of a linear combination of the data and outputs it to the next step of the model. And I'm going to show you on the next slide about how that works. So that's the functional form. It doesn't look like regression. It looks like a nonlinear function of something that does look like regression. But then we're going to do that repeated number of times. And that's apparently motivated by how a neuron works. So, you know, you've got the impulse carried to this particular neuron. It goes down the axon and then sends more information out. Okay. Well, if you combine a whole bunch of equations like that, so the red here would be your X data as input. Each one of these dots represents a different variable. And then you combine them in ways take nonlinear transformations of them, and then combine those, and you'll get an output. The reason that this type of modeling got a lot of attention early on is because it has very nice theoretical properties. This way of modeling data can be shown to be able to approximate any function. Okay, so there's mathematical reasons why this kind of framework is very elegant. But it stayed in the computer science literature and statistics literature for 20 years before it started being used, because computationally it's very, very slow to do approximations for really complex functions. Then when deep learning came along and said, okay, rather than trying to just make many, many combinations of functions, let's do this idea of making layers of functions. So a function of a function, a function of a function of a function of a function. And that turned out to work really well, in particular for processing images and speech. So signal processing, this way of approximating the functions works really well. It can be done quicker, and it really was what sort of led to the sort of revolution of being able to have good speech recognition and good facial recognition quickly. It's because this complex function of data could be processed quickly. All right. Well, with a very complex function like that, we can run into what's referred to as overfitting problem. So the model may predict the current data set very well, but may not generalize to the population or even to the next data set that comes, the data point that comes along. So for a given data set, a complex model might overfit, a simple model might underfit. What are we to do? This picture is just meant to represent the problem. So let's say you wanted to be able to separate the blue dots from the red dots. Well, one way to do that would be to draw this curve, but of course you're not going to get perfect separation. Another, in a neural net, would easily find this green path, which perfectly separates. But then when you get a new data point that comes along, it's not going to know where to place it. Okay. So the question is it the green line or is it the black line? In machine learning models, the way we often go about trying to determine that is using what's referred to as cross-validation. So you take your data set, you split it up into what's referred to as the training and validation data set, and then the test data. And so there's a training stage in machine learning models and a testing stage in machine learning models. During the training stage, you have the input X, you somehow iterate throughout the algorithm that is finding sort of the best functional form over here, iterates by asking how well it works, how well the model predicts this one validation data set that you keep out. And then what you do is you iterate and you do that over and over again, changing which one you're leaving out. And you do that in order to get your best model. Okay? Then, to assess the quality of your best model, you take the input X from the data set that you held out, the test data that you held out, use the model you got from the training stage, see what the best guess was for Y, and then compare it to the actual correct Y. And then you can actually cross-validate this in order to get the measure of the out-of-sample prediction accuracy. More and more, we're seeing challenges for machine learning models where the test data is actually held out by an agency or by a foundation and then kept under lock and key. The rest of the data is given to people to try to train the best model, and then you go and see how well it works on the test data. I think, honestly, that's the only true way to really keep, keep the modeling method honest. Because it's easy, while doing this procedure, to sort of let this test data creep in various ways into the model building itself. Okay. So sidebar for a second here. So I've been talking about coming up with really good models for prediction. And I started off by talking about explanatory models. Well, you might think, well, if I have a really good explanatory model of how the world works, then it should work well for prediction. The fact of the matter is that isn't in general true. And indeed, our search for different kinds of imaging biomarkers that we will hopefully eventually help explain, causal relationships between variables of interest. This very nice paper written by Guillermo and Anissa demonstrate that indeed, like a statistically significant difference on a biomarker does not necessarily translate into good predictive power. And I think this is an important point to just have in everybody at the back of your mind when thinking about switching to thinking about problems for prediction. And they have this demonstration. And I work some with Guillermo, and I just wanted to congratulate him on such a clear explanation in this paper. I just think it's so nice. So they say, okay, we're in our search for describing psychopathology, we're looking for biomarkers. That's what the paper is more general. This is just one nugget, by the way, of this paper. This paper is, everybody should read this paper. It's a good paper. And this is just one nugget. So in this search for biomarkers, there's many things to consider. And here they're pointing out that even if you can find a good biomarker, it might not be good for prediction. So let's say you have a biomarker here, and its distribution in the control group is up here, and in the patients is down here. So if you were doing a hypothesis test there or estimating the beta coefficient, you would find a Cohen's d of the difference here of 1 standard deviation. So that would be a large effect size. On a lot of the projects I work on, we hardly ever get Cohen's d's that big, right? We're happy when we get 0.4. So this is the distribution of the two. Here's what the distribution looks like with a Cohen's d of 2. And here, this is meant to just show that indeed, if you don't have equal numbers of patients and controls, even with a Cohen's d of 2, the difference looks like this. What is this meant to show us? There's a very large overlap here. So even though these two groups are different by 2 standard deviations in mean, there are many people in the control group who have scores that are in the range of the people who are patients. And they go on to show that indeed you need to have a Cohen's d up near 5 if you have something that's only prevalent in the population of 1% before you even get to a 50% posterior predictive value or positive predictive value for that biomarker. So you need really big effects to do good for prediction. All right, so what are some of the things to consider with machine learning models for prediction besides that point? One is generalizability. Depends on the data used to train and test the model. Does it look like the population you want to use it in? So that same problem that we have whenever we're trying to think about the data we're going to use for a problem is whether the results can be generalized depends on what the data was that went into it. Interpretability. This is really still an active area of research. We have measures called like model reliance or variable importance that can help us to try to interpret something about these black box models, but it's still very difficult to interpret the model itself. Feasibility. So given you've trained a machine learning model, will all the needed features be available when you really want to do predictions in the future? If your model relies on things that you're not going to be able to collect when you want to use it, then the model is not going to be very helpful. And then in machine learning models for prediction, we really want to think about how the predictions are going to be used in the future and thinking about interfaces for how that would be done, whether it would be necessary to update that model in the future. I want to now turn to sort of 2 areas, or 2 examples. There are many examples I could have given, but I had too much that I wanted to say in this talk, so I tried to focus on 2 that have gotten a lot of attention in the recent psychiatric research literature. And that is, one is predicting suicide attempts, and the other is classifying psychiatric disorders with neuroimaging measures. So this is hard, right? It's hard to make predictions, especially about the future. Apparently, we don't know who that can be attributed to. Some people say Yogi Berra, others say others. But apparently nobody ever said this. I said it. Maybe someday it'll be attributed to me. So in suicide, there's a very long literature of trying to look at predictors of suicide. And a recent meta-analysis by Franklin in 2017 summarized 365 studies to predict suicide and found that across all of those, despite the fact there are a lot of risk factors identified, For the purpose of prediction, the AUC was on average 0.58. And in that paper, really sort of calls to arms saying maybe we want to do something different. Rather than focusing on identifying risk factors, maybe we should recognize this is too complex for us to figure out and just try to see if we can predict. So like Bremen said, forget about nature for a minute and just see if you can predict the outcome. And so really, a flurry of articles since 2014, and I want to thank Hanga Galfalvi for putting this slide and the next together, just summarizing some of the different things going on, but it's been a real methodological shift in this area of trying to predict suicide. We've seen, in the popular press, suggestions that now we can predict suicide with really good accuracy with EHR data. I think the jury's still out on whether those sorts of things are going to be reproducible, but indeed, they're relying on big data, including EHR, social media, text monitoring, and different types of streams of information you can get about a person in order to try to predict suicide. And the range has gone up a bit more. There's been some, prediction summaries that are up in, the 0.9 range in terms of the AUC. So that's much better. And indeed, there's a lot of this type of research going on here at PI. With Barbara, I know that you guys are working on EMA for suicidal ideation in borderline. EMA is when you're ecological momentary assessment where you're asking people questions throughout the day. And so how are you feeling, et cetera, what was stressful events, and trying to use that to predict suicidal ideation. And then with John Mann and others, high dimensional clinical data trying to predict suicide, genetic biomarkers, and combined with EHR data that Hanga's working on with the Million Veterans Program. And then, Maddie, I know you guys are doing something with help chat line data, trying to see if there's a way to extract information from the chats that would be indicative of different types of suicidal behavior. Also, classifying psychiatric disorders with neuroimaging measures. So this also can be seen as a prediction problem. Classification is effectively a prediction problem. And it makes sense, brain disorders, maybe we should look at the brain to use that to measure the disorder. There's been many meta-analyses done recently summarizing a lot of the work that's been done in neuroimaging classification of disorders. So this one in 2015 summarized a slew of articles using structural, functional, and diffusion, MRI, and what different types of classifiers, machine learning classifiers they used, and the accuracy. I thought this was very interesting, actually, to sort of see the summary for schizophrenia. There's been a combination of using either structural, functional, as well as diffusion to try to classify someone as schizophrenic versus normal using the neuroimaging data. Mood disorders, anxiety disorders, ADHD, autism. These are different disorders that people have been trying to classify using neuroimaging data. Actually, if you see here, you see the dominant method that has been being used has been actually support vector machine to do that because it's a very flexible way to deal with high dimensional data. But then there was another meta-analysis done just last year in the neuroimaging that summarized a whole bunch of other meta-analyses. So there's been, across the different studies, this Wolfer one is the 2015 study, and this is the summary of all the psychiatric diagnostic studies that they had found. But actually other articles have found even more in the literature. And this paper is a very nice one that summarizes the problems. That is with sample size. And so they actually find that larger studies are actually producing less accurate predictions. So you might think, oh, well, I thought big data, I'm supposed to have bigger data to be better predictions. Well, this is the difficulty. There's a lot of variance in prediction accuracy, and there's probably also publication bias, right? Those smaller studies are only getting published because they show good predictive accuracy, but maybe they just found good predictive accuracy because it's a small study by chance. Also, as the sample size increases, it might be an issue of less homogeneity of the populations and also less standardization of the imaging measures. I want to, in terms of the spirit of, well, what, there's been all this success with machine learning in other fields. So why hasn't machine learning been able to cleanly diagnose psychiatric disorders? Why can't we do this? Why can't we feed it an image, and get it to find out what disorder somebody has? Well, in all the other fields, that this has been used successfully, the humans are the ones providing the labels by looking at the image. So in mammograms, a radiologist looks at the mammogram in order to diagnose whether there's a tumor there. In object or face recognition, I can look at an image and know who that person is, and I look at the image to decide that. In other fields, the input into the machine learning is the same data that's used by the human to label the image. So the machine learning algorithm is able to be trained to classify images as well as a human. And maybe better because they can do it much faster than a human and without cost. But in psychiatry, the disorder labels are not determined by looking at the brain image. Disorders are diagnosed by clinical evaluation and self-report, not by reading a brain image. So classification by neuroimaging is trying to train the computer to do something a human cannot do. And so that's why it's hard. So I feel like there's all this excitement like, oh, we just don't know how to use the tools well enough yet to solve the problem in psychiatry. Well, I would say the problem is just harder in psychiatry than a lot of the things that it's been used for so far. Okay. In the interest of time, I'm going to skip to this. So I mentioned in the beginning there's sort of three main objectives of scientific research: explanation, description, prediction. And when we think about how big data and machine learning come into that, I described that I really think that it's been so far helpful for us to think about describing the context better, or identifying things that are really different in terms of phenotyping, and as well for prediction. My hope is that eventually we sort of can bring in the explanatory and causal understanding into that. The vision of the future, this might be one vision of the future. We have a person, so in terms of like precision medicine, we have our person. We collect all this big data on the person. We put that information through some machine learning model. We recommend an action. That machine learning spits out, here's what I think the best action would be for that person. Maybe start a treatment. But then we're going to keep learning. So after you start the treatment, you monitor the action and collection through some kind of digital data stream as well, and keep this going. So this would be, I suppose, the vision of the future of how machine learning could contribute to a sort of precision medicine future. So what are some final things to consider? First is explanatory models, which we have spent a lot of our scientific research efforts on, in terms of thinking about how things are related causally, might not necessarily be good for prediction. And prediction models are not necessarily good for explanation. And I think that is something we need to work on. We need to improve and develop methods to facilitate their fusion, to have sort of explainable prediction models. Then diagnosis and prediction in the real-world clinical populations is much more complex than in research settings. So, a lot of research settings are set up like 50% patients, 50% controls. The real world isn't like that. So we have unbalanced information coming in the real world. We have comorbidities. We're probably more interested in differential diagnosis rather than just saying different from healthy. And we really need more studies to tackle those types of problems. We also want to think about the trustworthiness and the quality and the reliability of the data that we're using, particularly from health records and other big data sources. And we need standards for that. And finally, there's ethical concerns. So, thinking about the financial incentives that may influence like what data we're actually able to get in the first place. And, issues of privacy. If I'm being monitored all the time and someone's running an algorithm to figure out my next step, that really becomes an important thing to think about. And then, the hope of precision medicine, my picture that I just showed, well, actually that might increase disparities. I mean, one might think, okay, precision medicine is going to be great because we're going to be able to use data and we're going to be able to diffuse more information, but indeed it might be that only certain types of people are able to get that type of data, and in fact, disparities might increase rather than decrease. So afterthoughts from that same article by Simon, he said there are both exaggerated hopes and exaggerated fears that big data and machine learning will supplant human clinical intelligence. Both the hopes and fears stem from really overly optimistic expectations that data quantity outweighs data quality and that artificial intelligence can spin straw into gold. And I want to say that I think there's still many important psychiatric research questions that can still be answered without big data and without ML. I don't think we all need to start using big data and ML in all of our research questions. And then finally, I really need to always, I can't stand before an audience of this size and not beat the drum for reproducibility. So reproducibility was already a concern, and Lisa made some comments about Susan's work in terms of being very rigorous. That's already been a concern for a long time in scientific research. It now needs to be even more attention placed on it as the data and its analysis is even more complicated. And so I would say it's an exciting time to be a data scientist. And I want to thank my group from Mental Health Data Science. We're all data scientists, and we have a large group of graduate students working with us from the Mailman School of Public Health. So thank you. That's it. Sorry, I went over.
Oh,
Maybe I can stand over here.
don't go anywhere. Questions? Melanie, thank you so much. That was really remarkable, and it's gotten me thinking also a lot about characterizing service delivery issues, but I'll see if others have questions. Yeah.
Thank you, Melanie, for that great talk. Congratulations on your award. I have a million questions and many, many challenges, but thinking clinically, though, I mean, does one necessarily need a perfect predictor, for example, to decide what medication a patient should be taking? For example, if you can improve the prediction by maybe 5% or 10% about, say, what medication you give or what kind of therapy you give, wouldn't that still be a step in the right direction?
Yeah, is this on? I think it's a good point. I think that I certainly don't want to leave you with the belief that somehow we even doing a little better in prediction is not a good thing if you can't do perfect prediction. I didn't mean to say that, when I said prediction is hard, I don't mean it's impossible. And improvements in prediction is a good thing. I think what's important, though, is to think about, how much better does it need to be before it's sort of worth making those types of decisions and acting like the machine, the prediction being a little bit better makes us gives us too much confidence. So my concern there is more about that hope, like being too hopeful that a slight improvement in my prediction means I'm making a better decision. I think the clinical importance of that really needs to play in. What I don't want us to start to do is to think like, oh, well, we play around with p equals 0.06 versus p equals 0.04, and we start getting excited about a p equals 0.04 because it reaches some threshold, and 0.06 where we say, oh, well, what can I do different to squeak it by? I think it's the same thing with prediction, a little bit better prediction. I'm not sure it's worth getting that excited about. I think what we need is ways of interpreting that. Right now there are not good tools to think about things like number needed to treat, which we have ideas for thinking about that from other fields that would be useful at the individual level. Like how much more sure should I be before I decide to make a change? I don't have a good answer to it, but I understand that we need to come up with a good answer for that.
I just wanted to make a I didn't so much had a question, I more wanted to make a comment, which is just to reassure you, Melanie, as usual, you exceed expectations. So that's what I would like to say. And it's an incredible pleasure to have you as the head of our area of data science. And your leadership has really been remarkable. And I now also get, having just been looking at your other support, because our progress report is going in and thinking, oh my God, she can't be on all these grants. But I see that you categorize them in these three ways, which are explanatory, which are descriptive, and which are predictive. And so I now see that you see us all in three buckets. And I see how you can sort of, which I didn't realize before. And I also just want to make a comment of thank again so much to Susan Essock, because without this endowed lectureship, right, this is make sure that what stays front and center in our department, which is a really important part of our department, but what stays front and center is this bringing science to real practice. So I just want to, again, thank you, Susan, for making this possible.
Hi, you're going to get a lot of smart questions from smart people, but here's a really dumb one. I'm just trying to engage with this wonderful presentation. A big problem for psychiatry is figuring out, is the whole problem of suicide and what to do with suicidal people. And I know we have a Columbia scale, and I know there's some really, I don't know if Barbara or John is here, they can tell me that this is even dumber than I think. One question I've had is, do we have any idea whether holding on to somebody who says, yeah, I've got a lot of thoughts, or even made a suicide attempt, do we have any idea whether holding on to somebody for a while, rather than just sending them out, makes any difference at all in terms of outcome? Now, we know a lot about what happens right after we send them out, but my question is, should it be, and you can't study this because nobody's going to have the guts to just send everybody out right away, although I've done a lot of that. But my question is, should you be able to design a study using machine learning that could help answer that question without having to carry out such a study in the real world, if you see what I mean, without having to try this?
Yeah,
It would be very helpful.
I don't know
if you
the
could.
answer to the suicide question, but in terms of the designing the study, one of the ways that, there's been a lot of progress in observational data analysis. And a lot of that progress, in using it to answer causal questions like what you're asking. And a lot of it has to do with taking data sets and constructing sort of scenarios in that data set that mimic trials. So you utilize propensity score methods and expanded versions of propensity score methods to take rich observational data and sort of select certain people in that data set that could be representative of what you might get in a trial. And actually, we've done that in different projects using this type of EHR. So for the explanation, I didn't talk about that, but you can use these type of methods to get towards explanation by mimicking experiments using these models. Frank? Or Claude? Bill?
Sorry. Wonderful talk, as usual. I think you brought up something really important, which is, deep learning, machine learning isn't some, magical potion. It's statistical learning. It's an extension of it, and it's an application that's been defined in my field in imaging very clearly with convolutional neural networks in 2D spaces, and most recently got exciting once GPU prices went down and all that other stuff. But I'm just wondering, we're using statistical methods of labeling that are informed by certain priors that have no kind of machine learning backing. They're informed by just
The DSM.
which is bed measurements, right? But the idea is, no, I meant objective, like if you just have an objective measurement like imaging, there's no, what we're seeing in neurology at least is the label helps inform, or the objective measure, let's say hippocampal volume, helps inform the image, and we train and we discover hippocampal volume is down based on some deep learning approach. But what we're discovering is that people who are mislabeled might have been mislabeled clinically. And I'm just wondering if we can kind of reverse engineer like machine learning in a way where, or your thoughts on this just in a forum, whereby the label is informed by what we're gaining from machine learning to help correct what we're, like misdiagnosis, or if, again, for Alzheimer's, a patient's CSF levels are high, but they were mislabeled or potentially mislabeled, but machine learning caught that. I'm just
Right.
wondering if you have thoughts, because with bigger data sets that we have access to now, we're kind of learning some really exciting stuff. So.
Right. So I focused on the sort of supervised learning problems when I was describing things today. I think what you're talking about is really what we generally refer to as unsupervised learning. That is, try to learn the labels or try to learn new ways to label people based on the data itself. And I think that there's a lot of opportunities. So my answer to you is yes, I think there's things we can do in that realm. And indeed, it's what we're trying to do when we're trying to say, take all this information and see if there's a new way to organize people. When I say organize them, I basically mean label rather than MDD, OCD, healthy.
Thank you, Melanie, for such a wonderful talk. In my field of perinatal mental health, we are seeing more and more big data studies and not so much machine learning so far, but one of the things that has been troubling is in a field where there are many, many potential sources of bias, you're getting a lot of big data studies that I think are sort of people are interpreting as making predictions or as causal explanations that are not. And it's also, as someone who has a clinical content expertise, I get asked to review papers where I know that I don't have the expertise to look at the statistical analysis. And as we get into more big data and more machine learning, I'm wondering what your thoughts are about the peer review process in all these publications and how the impact of this sort of more and more specialized knowledge. If you think about, if I was thinking about your slide with the 3 circles, concentric circles of hacking, expertise, and then biostatistical knowledge. What your thoughts are about the peer review process in this context and how that might need to change over time?
It's an important question. I don't think I have good answers yet, although I would like to just draw the parallel to even the traditional methods that, I hear regularly that different journal editors are asking if we can get sort of more statistical reviewers to help with traditional methods. So I think it is a problem. I'm not sure how to think about coming up with a good solution for it. Other than, one thing I would like to say is that I really like my job here. I like being a statistician. And the reason I like my job here is because I get to be a statistician for real problems, right? And I think as a field, statisticians don't always, there's been I don't want to sound bad, there's been an older school camp who wasn't as into being part of the real problem, and they were maybe more into the method and theory themselves. And if somebody was going to use it someday, that's good. I think this sort of embeddedness of a statistician and a statistical team within an applied area greatly helps with that particular issue, because you have statistical insights sort of working hand in hand with the researchers there, and also people who you can call upon who would be willing to say, review the statistics in a paper like that. So I think that, and I believe that more and more as biostatistics has grown out of statistics, and now data science is somehow coming a new thing as well, that's an even more applied version of statistics, we're going to have more people like me who are available to be thinking about these methods integrated with the scientists than we maybe did, say, even 20 years ago when I was starting PhD in statistics. I think there was a lot more separation. And so hopefully with the integration of data science more into the applied fields, that'll help that problem. But I don't have any other answer.
For sure, we need more people like you, I think, is the answer.
Yeah, well, more structures like. Yeah, I would say, I appreciate all the nice things said, but I wouldn't, all those nice things couldn't have been said about me if this institution didn't exist the way it exists, with a structure where we have support for biostatistics, sort of centrally, in order to reach out and help the different groups.
Hi, Melanie.
Hi, Tom.
I just wanted to say thank you very much. It's amazing that this is a talk about statistics.
And people are still here.
and it's so good. And wearing my OMH hat as a senior policy person for the State Office of Mental Health, I just want to say how lucky we are to have you on our team, and we want to get you more involved, I think, on the state side. There's some examples that came to my mind as you were talking. The State Office of Mental Health faces some real, very interesting challenges and goals in terms of the structure of the state's public mental health system. You know, we want to implement and scale up services for first episode psychosis statewide and cover the needs of the population-based estimated needs of people with new onset psychosis. How do we know we're doing that effectively and accomplishing our goals? I think you can help us with that. We have a state psychiatric center inpatient program of over 3,000 beds that historically have been custodial care, and we're in the midst of an effort to really change the culture and shift the approach of care such that it's fundamentally more modern, acute, et cetera, and lowers our length of stay and gets more people out into the community. How do we know we're doing that? We're very anxious in the Medicaid program in New York State. There's this major shift in the funding approach towards these value-based models. We could talk about them when we have time. But we are very worried that there's going to be unintended consequences. The most worrisome would be a markedly diminished access to care amongst people with serious mental illness in the state based upon the incentives of this program statewide. And so that's a program that affects 6 million people, of which 1 million of them receive services for behavioral health conditions every year. How can we understand whether those 1 million people have greater or worse access to care with these policy initiatives? So we really need to take advantage of what you offer. Marlene is here. Marlene Radigan, where are you? There she is. Marlene's the director of the Office of Performance Measurement and Evaluation for the State Office of Mental Health, and Marlene's team is tasked with trying to understand these major transformational initiatives, and I think we can really use you in this approach and look forward to doing that. So thank you again. I'm sorry I'm not asking a question.
No, that's okay.
Complimenting you.
And I'll just say, we're trying to build those partnerships already, actually, under Lisa's leadership with the potential EpiNet. We might be actually being able to do that sooner rather than later.
So I have you want to go? So I speak as an early fan. We had a neural network club here in the Institute in the 1990s even. But the interesting thing to us was that as you go beyond the layered, the back propagation models, and you get into these, isn't it called the Hopfield nuts, and the ones that are analogized to the congealing of glass, and they have all kinds of chemical metaphors. No one can follow what they do. You can't lift the hood on these things and see what they're doing. So I'm very interested in the reverse engineering question that came up before. Is there any research on how to work backwards from these things? Because I'm not saying we shouldn't take them on faith. I do believe in them. But in a way, it's like hocus pocus. And they say that a sufficiently advanced science in any culture would be seen as magic. But I mean, that's a science fiction claim. You understand what I'm saying? Is there any research being done? Well, you explain. You know more.
Yeah. Well, no, I don't. First of all, as I said, I'm a student of this as well. So I feel like every minute there's something else to learn in this area. So, and to the question of interpretable machine learning models, it is an active area of research. There was a presentation last fall in the Data Science Institute downtown of someone who was talking about doing just that, sort of taking the predictions and literally doing a kind of backprop through the model to find out what features might have existed in combination that could have led to the prediction. It's a hard problem in terms of the mathematical tractability of it, but it's an important problem. I can also say that I know it's an initiative actually at NIMH. Michael Ferranti's program in computational psychiatry recently was saying what we need to do is do a melding of sort of computational models that are explainable with data-driven models, and he refers to it as XAI, explainable AI. And there's a call right now from NIMH to work on exactly that type of problem. How can we take information that we do know and combine it with these complex data-driven prediction models to sort of learn something about it? And I don't have the expertise in it yet, but it's a burgeoning area, right?
Thank you very much. Stephen Heiler, and I'm a big fan of technology. A question that comes to mind about when using big data is who owns the data? And you spoke about privacy, but like for Medicaid data, is this data owned by the state? Where does the patient fit in? When you have data that winds up in a medical database from a hospital or an insurance company, who owns that data? And who has access to that data? And what does the patient have to say about all of this?
Great questions. Is Paul here? No, I don't think he's here. So I don't have answers to any of that except to say that right now there's a lot of work in the ethics field, like trying to think carefully about whether we should be creating sort of standards for thinking about that, as well as guidelines for thinking about that. And IRBs are considering these kinds of issues. Those are all good questions. I think I just leave them as questions. I don't.
Or high tech have anything to say about this?
Is HIPAA or high tech? I
mean, data,
yeah.
involved in these issues, but is there any federal or
Yeah.
state regulations?
Yeah.
I mean, I think
Go ahead.
we're at a crisis of there are two things in our field, right? And one is this whole thing of big data, and the other one is this whole thing about privacy. And I just think we're at this crisis here, Steve.
And probably our protective models are not adequate to really kind of answer the questions. I think we're about out of time, and I wanted to just make one concluding comment, which is again to congratulate and thank Melanie, to thank Susan, and to say something that you kind of alluded to, but I want to also underline, is that Melanie is working with a number of her staff and trainees who I just also want to give a shout out to, to Melanie for doing the teaching and the mentoring, because obviously we need a team of people to be doing this work, I think, with the kind of curiosity and rigor and kindness that you bring to the question. And I see some of the folks that I've had the privilege of working with, and I really want to make sure that we appreciate that part of the work you do as well. So thanks, everybody.
See your very first page was that old research article.